Alright, hi guys, I'm back. My name is Wilfrid, and I am a senior math tutor, and I'll be going through some calculus questions today, so primarily around grade 12 to level 1 university math. So I am a recent graduate of McMaster University. I graduated with a major in biochemistry and a minor in mathematics, and today I'll be covering around 8 questions, and yeah, I hope you guys learned something today, and I hope that you guys take something out of this lesson. So let's begin. Oh, okay, cool. So the first question that we're going to cover today is how do you find the critical points of a function? So there's a few things to define first. What is a critical point? So a critical point is a value of f prime of x, and x of f prime of x, where f prime of x equals 0. So this is kind of the definition of a critical point of a function, but it really does tell us a lot about the function itself. And I'll kind of describe what I mean. So if you guys are not aware, mostly every function should have its own derivative, and many continuous functions have a derivative. So for example, let's say that our function is y equals x squared, which is a parabola. So it looks like this. Okay. So its derivative will tell us the nature and how this function will behave on the real value domain, I guess, or the real number domain. So we all know that its derivative is y equals 2x. So we'll be covering how to derive things later on in the lecture or in the lesson. But right now, as of now, we know that the derivative of x squared is 2x. So this resulting derivative function gives us a look at how this original function, or parabola, behaves. And the critical point, as we described before, is the values of x of f prime of x, or the derivative of our function, where f prime of x equals 0. Okay, so there's only one point here, and it's at 0, 0. And what these critical points, or these critical values, tell us is that at these critical points, the slope, or the behavior of the original function is 0. And that means that it's not increasing, it is not decreasing. And these points are of very, I guess, of interest, because there's a lot of ways that we can apply the critical values to different kinds of mathematics. So going back to our board here, so the junior tutor kind of laid out the steps of how to find the critical values. And then they gave us an example, and they posted us an example. So I'll run through all of this with you guys right now. So it says the following are the steps in finding the critical points of a function. First of all, find the derivative of the function. So in our case, I'll use our example. Our function equals x squared. Okay, that's our function. So our derivative, and from now on for the entire lecture, I'm going to call the derivative f prime of x and the second derivative f double prime of x is equal to, is equal to 2x. Okay, so that's our first step. We have found our derivative. So let me just write this first step. Okay, so we have found our derivative. So the next step that the junior tutor lays out here is set f prime of x to 0. So we're going to do that now. So second step, we're going to set f prime of x to 0. So if sets f prime of x equals 0, and if we set f prime of x to 0, we have this resulting equation here. So we have 2x equals 0. Okay. So the third step, solve for the values of x that make f prime of x equals 0. Well, there's only one solution to this equation, and we know that x equals 0 when f prime of x equals 0. So one solution, and that is x equals 0. Okay, and finally, you want to substitute this value of x into our original equation, f of x, to find the resultant y value of where that critical point is. So the fourth step is sub this solution back into f of x to find resultant y value. Okay, and once you sub it in there, that is your critical point, and that critical point corresponds to the fact that at that point the behavior of the graph is now not increasing or decreasing. So the slope is 0, basically. So the junior tutor, they use a slightly more complicated example. They use f of x equals x to the 4 minus 8x squared plus 16. And they found a derivative. They set f prime of x to 0. And they found 3 solutions. So they found 3 critical points. And they plugged all these 3 critical points back to the original function to find the critical points where the graph, where the slope of the graph at these points are 0. So this is a good and detailed solution. Nice work. Cool. All right. So I kind of laid it out with x squared because this is a very simple example. But that is the general baseline of how you find the critical points of a function. There are obviously other ways of finding it by using its second derivative, but we're not going to cover that here. Okay, so we're going to move on to the next question. All right. So now that we have talked about finding critical points, we're now going to talk about the first basic rule of deriving functions. So the question reads, what is the derivative of 1x squared? So before we even begin the question, there are around 3 basic rules of deriving. There's the chain rule, actually there's 4. There's the chain rule, the power rule, the product rule, and the quotient rule. So in our specific example, we're going to use the power rule to find the derivative of this function. So let's define this function first. So let's say that f of x equals 1 over x squared. Okay. Brackets. Cool. So we have defined our function of f of x equal 1 over x squared. Okay. So the power rule suggests to us that the derivative of any variable with a power on it can be described as such. So let's say that f of x equals x to the power of n. Okay. So if our f of x equals that, then f prime of x equals n times x to the power of n minus 1. Okay, so this is what the power rule describes. If our function is of the form x to the power of n, then our derivative is taking that exponent down and subtracting the exponent by 1. So that is our derivative. So going to our question in specifics, so we have f of x equals 1 over x squared, right? We could alternatively describe 1 over x squared as x to the power of negative 2. This and this are equivalent to each other. So now we're going to apply our power rule. So now the f prime of x, we're going to take this negative exponent, as you guys can see here, we're going to move it down as a constant multiplying this variable. We're going to write our variable, and we're going to say negative 2 minus 1. And the final function is negative 2 times x to the power of negative 3, and I'll write it back in original form, which is this. So this is the derivative of our function f of x. So the junior tutor basically wrote the same solution as I did, and he got the same, or they got the same correct answer. So this is the correct answer. Good job. Cool. moving along. All right, so we're going to take a step back from deriving or explicitly deriving equations, and we're going to talk about a technique called implicit deriving. Okay. So the question reads, how do you find an equation of the line tangent to the curve x cubed plus y cubed equals 36xy at the given point 18 and 18? So basically what they're asking us is that this point 18 of 18 exists on this curve. I can graph it for you guys here if you guys would like to visualize it. So x cubed, let me delete all this too, plus y cubed equals 36xy. So this graph looks like this. So it looks like a line kind of ish, but there's a loop here, and they're asking us, and if you guys want to see, 18 of 18 does actually fall here. So this is 15, 16, 17, 18, 16, 17, 18. So it'll be 18, 18 will be here. So this point exists on this graph. And what they're asking for us to do is to find a line that is tangent to this graph. So they're looking for a line equation, essentially. So essentially, this question is asking for a line equation. And what does it mean to be tangent? So they're looking for a line equation. They're looking for a line that is tangent or only touching 18x and 18y at the graph. So they're only looking for a line equation of that that's touching 18, 18, right? So we're going to be covering in a future question of what a secant line is. And a secant line is very different than a tangent line. So they're asking for a line of equation of form y equals mx plus b. Okay. Cool. So to find this line equation, we need the slope, right? And before we described that the derivative of any function will give us the rate of change or the behavior of how that function behaves, right? When it's increasing, when it's decreasing, and when it's not increasing, right? So basically, we need to find the derivative of this function here, and we need to find the slope at 18 and 18. And we find the slope at 18 of 18, we have our slope, and then we can find our y-intercept by plugging 18 of 18 into this line equation. All right, so I'll continue to explain as I go. But the thing is here is that there are two different kinds of differentiation. There's explicit differentiation, where we derive the equation in terms of a specific variable, and implicit differentiation, where we just differentiate not based on a specific variable. So let me explain. So explicit differentiation is usually the main method of differentiating, where we isolate for y and we differentiate for the independent variable on the other side. So for example, if we were to do this question, we would have to isolate for y. But as you can see here, it's pretty complicated to isolate for y, and it is actually very complicated to differentiate explicitly by isolating for y, right? If we were to isolate for y, let's say, for example, we have, okay, so I'll write our original function here, and I'm going to isolate for y, right? So we're going to need to do this, first of all, right? And we're left with this messy equation, right? We sub out y, and then we have, we still have a lot of dependent variable here, right? So this is possible to explicitly differentiate, but it's going to take a lot of usage of chain rule. It's going to take a lot of, I guess, brain power and a lot of clever tricks to be able to differentiate this. So implicit differentiation, in fact, leaves the equation as it is, and instead we try to isolate for y prime. And I'll show you guys how it works, okay? So the junior tutor here, they use the solution of implicit differentiation, so I'll also use it too. Okay, so let's say our equation is x cubed plus y cubed equals 36xy. Okay, so we're going to differentiate everything, all the terms here in terms of d over dx, okay? So d over dx of x cubed plus, dy over dx of y cubed, 36xy dy over dx, okay? Sure, we're going to differentiate in terms of everything, okay? And dy over dx just means we're going to differentiate the variable, we're going to differentiate y in terms of x, okay? So what is this x cubed? Well, using our power rule, we know that this is equivalent to 3x squared, okay? So how about this y cubed, right? So let's say that we know this y cubed is related to x in some shape or form, but we don't really know and we can't really isolate for it here, right? This is very complicated to isolate, right? So we're just going to apply a chain rule to this, and I'll explain a chain rule a little bit further down the lesson. So we're going to say, okay, so we're going to move this exponent down, so 3 and y squared. And the chain rule suggests that we differentiate the outside function and then the inside function. So now we're going to say y prime. Okay, so we move down the exponent and subtracted 1 from it, and that's our outside function. And then we differentiate our inside function. But we don't really know what it is, so we're just going to say y prime for now. Okay. Going over here, this is a product rule, right? This is x times y. So we're going to do x prime, which is 1, times y, so y times 1 here. And it's plus y prime times x, because the derivative of y is y prime. And x is just left alone. Okay, cool. So now we're left with this equation. We're going to isolate for y prime. Okay, so we're going to move the y prime over here. We're going to expand this right side too. So 3y squared y prime minus 36 y primed x equals 36 y minus 3x squared. All right, we take out y prime here and 3, and we get y squared minus 12x equals 36 y minus 3x squared. And finally, we move this term to the side. We divide the left side, or the right side and left side by 3. So we get y prime equals 12y minus x squared over y squared minus 12x. Cool. So this is our, so we implicitly differentiated. So we found our derivative of this function alternatively by just implicitly differentiating. And now we found the change of the function in terms of y and x. Okay, so now we're going to need to find a slope, right? So now that we have the derivative, we're going to plug in, we're going to plug in 18 of 18 in, because that's what's going to produce our slope. We have 12 times 18 here minus 18 squared over 18 squared minus 12 times 18. Okay, moving it up here. We know that these cancel out, so actually y prime of 18 is in fact just -1. Okay, so now, therefore, our line equation is now y equals -x plus b, and we just plug in 18 of 18 here, so plug in 18 of 18 to find our y-intercept, and that is 18 of 8 equals -1 plus, oh, sorry, this is -18 plus b, so b equals 36. Now we have found our line that is tangent to this curve, which is, therefore, the tangent line is y equals -1 x, -x plus 36. So that is our solution to this problem, and we came to the solution through implicit differentiation instead of explicit. So Do not try to explicitly differentiate this. This will be a mess. I mean, you guys can try. All right, so they also use implicit differentiation, and they also included a lot of they describe the power loop rule, the product rule, and they also describe the slope point form. So they implicitly differentiated. They came to our y prime, which equals this. They plugged in 18 over 18 to find the slope. And then they plugged the slope into the line equation, and they plugged in 18 to find our y-intercept, and then they produced the answer, which is the line tangent to the curve. This is a good, detailed solution. Nice work. Cool. All right, moving on to question number 4. All right, so this is more encapsulating, I guess, level 2 university mathematics, so advanced calculus. But I feel like this is a very important concept that we can teach today. So the question reads, how do you convert rectangular coordinates to polar coordinates? So another word for regular coordinates is actually the Cartesian plane. So the Cartesian plane, it runs on x and y, or whatever. So there's x and there's y. Okay, so this is what we call the Cartesian plane. So I'm going to write Cartesian. Okay, so this is where our rectangular coordinates exist. For example, if this was x here, so let me use different colors here. If this is x here, and this is the y over here, this resultant point over here is this resultant point here is point xy on the Cartesian plane, or a rectangular coordinate because it makes a rectangle, right? So let's do this. But alternatively, we can think of this rectangular point, or this rectangular coordinate, as a line from the origin to this point. Draw a line. So there's a line. That's a really bad line. Let me try again. All right, so we can alternatively think this rectangular coordinate as a line from that point to the origin, right? And what we have here is actually, we have a right angle triangle, okay? And we have a few pertinent pieces of information here. First of all, we have an angle theta. And second of all, we have a hypotenuse with magnitude r, okay? So what it means to convert rectangular coordinates to polar coordinates is we want to take our rectangular coordinates and transfer it to a different plane where the units for the x and y axis are instead r and theta. And the r, let me explain here. So r equals the magnitude of the hypotenuse, while theta equals the angle, okay? So we want to use the values of x and y to convert it into different coordinates with the magnitude of the hypotenuse and the angle, which is theta, right? So how do we convert that, right? So let me take another, and also, so let me get another, oh, okay. So let's say that this is our polar coordinate system, okay? This is our polar coordinate system, and the units for this is r, which is the magnitude, and theta, which is the angle, right? So how could we possibly take our x and y and convert it to r and theta? So let's write this here. Well, if you guys remember your trigonometry, Pythagorean theorem, R is essentially the hypotenuse. The magnitude of a hypotenuse is just the adjacent arm and the opposite arm, or x squared plus y squared square rooted, right? So the magnitude of R is just x squared plus y squared and a square root of that, right? What about the angle, right? What about this angle, right? If you guys remember your sine, cosine, and tangent angles, SOHCAHTOA, so sine is opposite over hypotenuse, cosine angle is adjacent over hypotenuse, and the tangent, or the theta for tangent, is opposite over adjacent. So we're given the opposite, which is x, or sorry, which is, yeah, x, and adjacent, which is y. So theta is actually related by tan of -1, x, oh, opposite over adjacent, over y. Okay, so, sorry, it's y over x. I am y over x. Okay, so our angle is defined as tan -1, or tan inverse of y over x, and our magnitude of our hypotenuse is related to the square root of x squared plus y squared. So now we can convert these xy coordinates into our new polar coordinate system, where this and this is theta, and this is r. And that's how you convert that to the polar coordinates. If you want to convert it back, for example, it's very simple. You just use the equations x equals r cosine theta. Because if you think about it, r cosine theta is adjacent over hypotenuse, right? So to find our x coordinate for a Cartesian plane, we just isolate for x, and for y, it's r times sine theta. So why is this important? So there are certain integrals that you have to calculate maybe in level 2 university mathematics, where actually converting to the polar coordinates is much easier to solve the integral or calculate the integral than to use rectangular coordinates or the Cartesian plane. So that's why it's actually advantageous to use the polar coordinates whenever you can. It's mostly primarily used when you're trying to calculate the integral of, I guess, circular objects, or a circular space enclosed by two curves or something like that. So, yeah, that's how you convert from the rectangular coordinates to the polar coordinates. So the junior tutor puts a very good description and a very good illustration here, and they also run through how to convert from rectangular to polar. And yeah, this is correct. This is the correct solution. Okay, cool. All right, moving along, we're going on to question number 5. So we're going back to implicit differentiation, and this time is actually explicitly asking us to implicitly differentiate. So like I said before, we can explicitly differentiate this function. So let's say, for example, y squared equals 2 plus xy, right? We can explicitly differentiate this, but it's going to look pretty hard, right? We have to move this one over here. We have to isolate for y somehow, and then we're going to need to differentiate. So instead, we're just going to implicitly differentiate, okay? So we're going to take d over dx of y squared, and we're going to take the d over dx of 2 plus xy. Okay, so if we're differentiating this, right, the chain rule again applies, where I'm going to use y prime from now on, where we take the outside function, which is, I guess, this function squared, so 2y, and the inside function, which is just y prime. Okay, so that's chain rule. This one is, so the derivative of a constant is 0 plus xy, so now I have to use a product rule, okay? So the product rule suggests that we take the derivative of x, which is 1. So let's do this. So it's x prime, which is 1, times y, and plus y prime times x. Okay. So now we're just left with 2y prime equals y plus y prime x. Okay, so we're going to isolate for y prime, which equals y. We're going to isolate, factor out y prime to have 2y minus x, y, and y prime equals y over 2y minus x. So you can see here that our derivative is a function of the original function and the independent variable itself. And that's different from explicit differentiation because when you find a derivative, that it is a function of only the dependent or the independent variable. Why is this 2x? Q y minus x. Oh, okay. So the junior tutor was pretty close to solving this problem, but in this one step here, they switched x and y for some reason, I believe. So this solution is almost correct. The last step, you accidentally switched. You accidentally put 2x instead of 2y. Yeah, so you can see here that they had here 2y minus x, but when they divided this left side and the right side, they put 2x minus y. So yeah, cool. So earlier on, I said that we're going to be calculating the slope of a secant line. So here we are. How do you find the slope of the secant line of f of x equals 1 over x through the points -4 and f -4 and 1 and f of 1? Okay, so let's graph this reciprocal function here just to visualize it. 1 equals 1 over x. All right, so this is what the reciprocal function looks like. And what they're asking us is to find the secant line of f of -4, which is here, and f of 1 and f of 1, which is 1 is here. So they're asking us to find the line, the slope of the line, and the line equation from here to here. So a secant line is basically a secant line, the line equation from 2 points on a function. So for example, if we had a quadratic function, we can say that, oh, give me the secant line from x equals 1 to x equals 2, right? So the secant line touches at least 2 points on the graph. And in this case, we want to look for -4, f of -4, and 1 and f of 1. Okay, so there's no need for us to actually use differentiation in this case. We can just try to solve for the slope by using the slope equation. So the slope equation is m equals y2 minus y1 over x2 minus x1. Okay, so we're going to need to calculate what x or y1 and y2 is going to be because they didn't give it to us. So let's do that first. So f of -4, if we plug it in here, is just -1 over 4, and f of 1 is just 1. Okay, cool. So now that we have our points, so they're asking for us to find the secant line between these 2 points here. Okay, this is a negative, and 1 and 1. Okay, So using our slope equation, we're going to say 1 minus negative 1 over 4 over 1 minus 4. Okay, so it looks like we're going to have a positive slope. So this is 5 over 4 over 5. So our slope, in fact, is 1 over 4. Just going to check that. Okay, cool, it's correct. And now we're just going to need to find the y-intercept. So going back over here, we have y equals 1 over 4 times x plus b. We're going to plug in one of these values. Let's just plug in 1 and 1. So 1 equals 1 over 4 plus b. b equals 3 over 4. So finally, therefore, our secant line from 4 to negative 4 to 1 of f of x equals 1 of x is y equals 1 over 4x plus 3 over 4. Okay, does that make sense to everyone? So the secant line is the equation of a line from 2 points on the graph, and it measures the slope from those 2 points. So yep, they got the same solution. This is the correct solution. All right, so let's move on. All right, so what is the limit of sine x over x as x goes to infinity? Let me just graph this function for you guys too, so we have some context of what this looks like. So y equals sine of x divided by x. Okay, so this is what that graph looks like. It kind of looks like a sine graph, but you can see that the amplitude slowly decreases as we continue on. And this is actually a very hard function to find the limit if we use substitution, if we use a regular limit rules, right? Like usually they're asking for this, basically, right? So limit of x approaching infinity when sine of x over x equals what, right? So substituting infinity into here and infinity into here, we get something very weird because this is a periodic function. So it's going to repeat over 1 and negative 1, and this is going to be infinity. So this is kind of hard. It's kind of hard to use our normal limit techniques to find our limit. So we're going to use something what we call the squeeze theorem or the sandwich theorem. So let me explain it to you guys here. Okay. So the squeeze theorem suggests that we can take, so let's say we want to find the limits. We want to find, let's say, we want to find the limit when x approaches infinity of a function. Infinity of a function. Okay, but this function is very hard to use our normal limit techniques. So instead, we can find two simpler functions to squeeze between f and x. So what I mean by squeeze is that we can find function g of x, which is always going to be less than f of x, and we can find a function h of x, which will always be greater than f of x, right? So as I explained further, you guys are not just going to need to guess this function. There's a way to find these kinds of functions. But if you do find these kind of functions where the output of g of x is always going to be less than the output of f of x, and the outputs of h of x is always going to be greater than the outputs of f of x, the squeeze theory suggests that if the limits the limits of g of x and limit of h of x equal the same limit, then the limit of f of x equals that limit. So this is what the squeeze theory suggests, okay? So we can use this theorem to help solve this limit, right? Because this is a very complicated limit and we can't just use the substitution infinity, we can't use conjugation, we can't use algebraic properties to try to simplify this limit, okay? So let's try. All right, so let's talk about sine, for example. Okay, for one, we know that sine of x is always going to be contained between +1 and -1, right? So we look at the function sine. Let me graph it for you guys. Sine of x. We always see that the range of sine of x is restricted to +1 and -1. There's never like sine x equals -5 unless you have some alterations to it. Okay, so we know that for a fact. Okay, so what if we divide everything in our inequality here by x? So what do we get? I'm not going to have a plus here. It's kind of redundant. Okay, so once we divide it by x, we have found a group of functions, namely 1 over x and -1 over x, that sandwich or squeeze sine x over x. This is just mathematically how that works. We can try to graph it out and see it, but by doing this clever trick, we have found two functions that sandwich or squeeze sine x over x, right? So now, what is the limit as x approaches to infinity of -1 over x, and same thing for what is the limit as x approaches infinity of 1 over x, right? We see here that this equals 0, and this also equals 0. So now that we see that the limit of -1x, -1 over x, and 1 over x equals 0, then by the squeeze theorem, we know that the limit of x as x approaches to infinity of sine x over x equals infinity. So that's how the sandwich theorem works, or the squeeze theorem. It's very, very actually useful for any of these sine or cosine functions where they're periodic functions. So yeah, that's how we use the squeeze theorem to solve this limit. Okay, so the junior student uses my solution, or I kind of use their solution, I guess. And so this solution is correct. Good job. Cool. All right. Finally, we're going to move on to our last problem of the day. And this is basic chain rule. So in the first question, we talked about power rule. So now I'm going to talk about chain rule. And the question reads, how do you find the derivative of y equals ln of 2x? So let me define what the chain rule is. So let's say that we have a function of a function, composition function, okay? So let's say that we have f of g of x, okay? So if we wanted to find the derivative of this function, right, f prime, let's say that is also equal to h of x. So let's say we wanted to find h of x. So h prime of x would equal f prime of g of x times g prime of x. So that is a chain rule. So to differentiate a compositional function, we take the derivative of the outside function and we leave the remaining inside function by itself, and we multiply it by the derivative of the inside function, all related to, I guess, a variable x, right? So how does it apply to our question here? Well, we see that this is a compositional function because we have a function inside the ln function, right? So if y equals ln 2 of x, right, y prime of x, I guess you can say, is the derivative of the outside function. So we know that ln of x, the derivative of ln of x is 1 over x, right? But instead of x, we have 1 over 2x because we want to leave the inside function by itself times the derivative of the inside function. So the derivative of the inside function is just 2. So the 2's cancel out, and we have 1 over x. So that's the chain rule. So the junior tutor used a different notation. I used Newton, and they used the Leibniz. But they came up with the same solution. They also used substitution, which is not necessary in this equation, this solution. But in the end, they came up with the same solution. So this is the correct solution. Good job. Cool. All right. So that wraps up today's lesson on some calculus and some derivatives. I hope that you guys learned something today. And I hope that if you guys have any other questions related to calculus, mainly grade 12 calculus to university calculus, please submit them to OneClass, and we'll try our best to solve them for you. But other than that, I hope that you guys learned something today, and I hope to see you guys next time. Thank you so much for listening, and I wish you guys I wish you guys a goodbye.